Hi, work and power. Well, work and power are two common words that are used in a lot of our everyday vocabulary, but they do have some significantly different physics implications. So let's talk about these things. What about the displacement caused by an applied force? So, like, let's say this guy right here, if you can't see it, he is in fact pulling a train with his teeth. So he's applying a force to move an object. Shouldn't it require more effort to push a box all the way across the floor instead of just pushing it out of your way? So, when you discuss force and the displacement it is applied, this is called work. Okay, a little bad English there, but so when we're talking about, guys, applying a force that causes displacement, we're going to call this work. Now, I really want to go back. Remember, last video, we did say some other things. We also said that work, now I want you to note this. This is in the last video. Work is also something else. Work is a change in energy. So we're going to have two different definitions of work, okay? Two different formulas. And they're both the same work, though. They're both the same. So work equals force times displacement. Now, it's very important that we note that this is displacement. These are two vectors. We're multiplying two vectors together. Now, the first thing to realize is that we have a force times a distance, or displacement. So that's going to give us Newton times meters. So once again, let's write up both of our formulas here again. We got work equals for change in energy, and work equals force times distance. Now the unit for this is joules. The unit for this is newtons times meters. And in fact, guys, if you write them all the way out, joules equals newtons times meters. So that's a very interesting concept to arrive at, that they're not so different. Force, displacement, energy, it's all connected. All these initial things that we've been talking about in this class are overlapping. Okay, so work requires three things though. It requires an external force. So remember, you can't push a car from inside it. Remember I talked about that? Hopefully your class was, got to experience that. If you think about sitting inside of a car or sitting inside the train is stopped on the tracks. You, inside the train, cannot push it forward. You have to be outside. It has to be an external force. The object must move as a result of the force in the same direction as the force. Now you see this little guy right here, and he's pushing on this sumo. Is he actually doing any work? And the answer is maybe. Because by this picture, I can't really tell. But I would assume that the sumo is not moving. Maybe he's absolutely stationary. Let's say that this guy is standing still. Let's say that this is not a picture, and this is a video. Well, this kid is pushing as hard as he can, and the sumo is not moving at all. I would say that the kid is doing no work. I mean, the kid is going to be extremely tired sooner or later, but he's doing no work because the force is not causing any displacement. So that brings us to our next thing. The object cannot return to the location it originated. So that means there has to be a value for your displacement. So like, let's say we take this box right here. Here's a box. Well, that's not what I wanted to do. Here's my box. And if I move that box around, and I take it anywhere I want. I take it here, and I take it there, and I go back, and I put a dot in the middle, and I delete that dot, and then I move it back here to this spot. If it goes right back to the original spot, what is the displacement? The displacement is zero. So if your displacement is zero, you've done no work. I know it's a little unfortunate. It's kind of a little depressing. Every day you get up, you walk to school, and then every day, hopefully, you return to the same bed that you slept in the night before. And in that regard, you have done no work moving your body around the entire day. I know it seems crazy, but this is the physics definition of work. It's actually you need a force, a displacement, and we're going to cause a change in energy. So, a force causing displacement and a change in energy. Now, let's say you're sitting there doing your homework, and then suddenly Mr. Shaw comes up and shoves you. Mr. Shaw, you complete jerk. Well, I just did work on you. It's very strange, I know. But let's say I just come up and I shove you, you get pushed. Before you were sitting stationary. Now I've given you kinetic energy, you're moving. I know it sucks, but I did work just then. Okay, let's go back to the PowerPoint. Going down some more, working out. Now, if we think about this weightlifter, the weightlifter lifts a 1,000 Newton barbell vertically 0.5 meters. How much work has she done? Well, this is 1,000 newtons. That's the force. This is the displacement. You would just simply multiply these two values by each other, and you would get 500 Newton meters or 500 joules. Once again, I would just simply go 1,000 newtons times 0.5 meters, and I would get 500 Newton meters or 500 joules. Awesome. Now, how much work has she done? Never mind. How much work would she have done if she lifted the barbell was twice as heavy? Well, twice as heavy means that this value right here is multiplied by 2, and that means she'd also do twice as much work. So if the barbell is twice as much, if you double the weight of the barbell, you double the amount of work. How much work has the lifter done if she lifts the weight 0.5 meters and then brings it back down to the initial position? So it starts right here. Let's call this point A, and she lifts it up to point B, but then she lifts it back down to A. And this, take a look. If you consider from going from A back to A, the displacement is 0, and she's in fact done no work. I know. Tell it to her face. Now, how much work is done if the weightlifter exerts a force of 1,000 newtons and the barbell doesn't move? Okay, does not move. Displacement equals 0. The work is 0. Okay, a little unfortunate, a little depressing. So we have a couple other problems here, like a cart vendor pulls his 250 kilogram cart, 85 meters of the force of this. What is the cart's acceleration? Well, I'd start off to do this one, guys. The first thing I would do if you were going to solve this problem, and it's important because you'll all be solving problems like this, I draw a free body diagram. So let's go back to my blank paper. I'm going to clear this off. Everything gone. So here's our cart. It's a terrible cart. Sorry, cart vendor. And he's going to apply a force. Well, we've got to draw the free body diagram, right? So here is the force applied. And here is the force of gravity. Oh, that's not what I wanted. Something has changed. Let's pause right there because I think I've messed with something.